This is a quick review of section 1-5. It starts with a bunch of song lyrics. If you knew Peggy Sue, then you'd know why I feel blue. That's an if-then statement. If I loved you time and again, I would try to say all I'd want you to know. C is if I had a hammer, I'd hammer in the morning. And D is if you want to make the world a better place, take a look at yourself and make that change. For popular songs of their time, each very different times. If-then statements are something we use all the time, and they're noted like this. This is what they look like when you're doing an if-then statement. It's called a conditional statement. This is called the hypothesis right here, P, and Q is called the conclusion. Another pair of words for it is antecedent and consequent. If a quadrilateral is a rectangle, then its diagonals bisect each other. You may actually remember that from geometry. It's not so much the if that's part of the hypothesis. It's the sentence, the statement here, a quadrilateral is a rectangle. And then the conclusion is not the then, it's just the statement here. Its diagonals bisect each other. So it's if P, then Q. And this is how we indicate in notation that it's a conditional statement. P implies Q. And so there are some examples here. If x is greater than or equal to 8, then x squared is greater than or equal to 64. And that's a true statement. Here's how the truth table goes. Right? And this is what we talked about the very first day when I was talking about if you clean your room, then you can go out, is very different from if you don't clean your room, then you can't go out. And here is how this works. If the antecedent is true and the consequent is true, right, or the hypothesis and conclusion, if they're both true, the statement is true. But if the first one is false, it doesn't matter whether the consequent is true or false. It's still going to be a true statement. The only way it can be false is if the antecedent is true and the consequent is false. So the only way that the if-then statement can become false is if the first part is satisfied and the then part is not. And that's what this says here. Suppose P and Q represent statements. The conditional statement P implies Q is false whenever P is true and Q is false. Otherwise, it's true. And here's the truth table that goes with that. And here's the same kind of example we used before. If your test scores total above 500, then you will get an A for the course. That means that really only what it says. If you get 501 or more, I have to give you an A in order to be telling the truth. But if I give you an A when you have a score that's lower than that, it's not that I wasn't telling the truth. It's just that I didn't address that issue with my statement the first time around. If P then Q, the negation would be P and not Q. Right? Because this says, right, the only time this is not true is if this is true and this isn't. So if I want to talk about the time when this is not true, which would be the negation, that would be this, P and not Q. And this is how you would express it symbolically. You've got the conditional statement here and the not sign here. Here's the and statement and not Q. Okay. And caution, you'll notice that this is an if-then statement and this one isn't. The negation of a conditional statement isn't another conditional statement. So if I said to you, let's just go back to the other one, if you get more than 500 points, then you will get an A for the course. If you want to negate that, then basically what you're saying is, I got more than 500 and I didn't pass the course. That's the negation. P and not Q. All right. So the negation of a conditional statement, if Tom lives in Springfield, then Tom lives in Massachusetts. Wait a minute. Tom lives in Springfield and Tom doesn't live in Massachusetts. How's that possible? Well, there are Springfields in all kinds of other places, which is why they chose Springfield for the name of the town in The Simpsons, so that nobody would know where they really were. So one of the most important types of statements in mathematics is both conditional and universal. For all x in S, if Px is true, then Qx is true. This is what statements like that look like in math, and here's an example of it. For all positive real numbers x, if x squared is greater than 9, then x is greater than 3. But if you make the domain larger, and you're talking about all real numbers, this isn't true because x could be less than -3, and that would make this false. And so if you were going to negate this, you would have to say, there exists a real number x such that x squared is greater than 9, and x is not greater than 3. Okay, so notice again, this becomes not a conditional statement anymore. It becomes, this is true and this is false. Right? And that's what we were saying up here. Let S be a set and let these be statements that may or may not hold for elements x in S. The negation of this is what we just said. There exists an x in S such that this is true, but this one isn't. Here is an example of that for all real numbers a and b. If a is less than b, then the cosine of a is less than the cosine of b. The negation of this statement would be, there exists an x in the real numbers such that a is less than b, and the cosine of a is not less than the cosine of b. Conditional is sometimes proved by establishing its contrapositive. In other words, the contrapositive of something is where you take the two parts of an if-then statement, negate them, and swap them. Okay, and they have the same truth value. Here is what that looks like. P and Q, if P then Q, they're all true except when P is true and Q is false. So this is what the truth value of the conditional statement looks like. If I negate them both and swap them and turn it into a conditional statement, then they're all true except for this one here, where Q is true, or not Q is true, and not P is false. So this result is the same as this result. So these are equivalent statements. So that means you could actually use as part of a proof the contrapositive of the statement you're trying to prove. That becomes a theorem. The theorem is a conditional and its contrapositive are logically equivalent. And then you've got converse and inverse. And they are described here. The converse is when you just swap the P and Q in an if-then statement. The inverse is when you don't swap them, but you negate them both. And then there's the biconditional statements. Biconditionals are if and only if, and they are the ones that go back and forth. If P then Q and if Q then P, right? It's read as P if and only if Q, and it's written this way because the if then statement goes both ways. And the truth is, this is actually the same as a definition. This is true if and only if this is true. It makes these two interchangeable the way a definition would be. All right, let's go to the questions here. If x be a real, or let x be a real number, and consider the statement, if x is greater than 1, then 2x squared plus 3x cubed is greater than 1. All right. Identify the antecedent. That would be this. X is greater than 1. The conclusion, 2x squared plus 3x squared is greater than 1. The consequent is the same as the conclusion, and the hypothesis is the same as the antecedent. Is the conditional true or false? Well, let's sort of think that through for a second. If x is greater than 1, then when you square it or cube it, it's still going to be greater than 1. And then if you multiply it, it's going to be greater. It's just going to keep getting bigger and bigger. So yeah, the conditional is true. All right, multiple choice. If Sandra is on the swim team, then she swims every day. Which would tell you that the statement is false? Well, before I even look at this, I know that if this is true and this is false, that's what's going to make it false. So it has to be Sandra is on the swim team and she doesn't swim every day. So which one is that? Oh, that's B. If Sandra is on the swim team, right, or Sandra is on the swim team and she does not swim every day, that makes this false. True or false, the negation of, for all real numbers x, if 2x minus 1 is greater than 5, then x is greater than 2. So we would have to say that the negation of this would be this is true and this isn't. And so what we're saying here is there exists a real number x such that this is true and this is true. No, that's not the negation. It would have to be there exists a real number x such that this is true and this is false. All right. In 4 and 5, determine whether the conditional is true or false. If false, give a counterexample. For all real numbers x, if pi over 2 is less than x, then cosine of x is negative. So if x is greater than pi over 2, then it's negative. Well, that's not true, because if you go all the way around, once you get past 3 pi over 2, the cosine is positive again. So that's not going to be true. If a quadrilateral is a square, then it is a parallelogram. Yeah, that's true. Right? Quadrilateral is a square. Right? Squares are parallelograms. They meet the definition. So here, if I were going to do an example of this, or a counterexample to this, I would just say, well, what if x is equal to 2 pi? If x is equal to 2 pi, then it's greater than pi over 2, but its cosine is 1, not negative. So that's the counterexample. Okay, so let's choose the correct word. And we have a choice of 3, contrapositive, inverse, or converse. And let's just go through them for a second. The contrapositive is when you switch them and negate them. Right? These are for conditional statements. If P, then Q. If you switch them and negate them, if not Q, then not P, that's the contrapositive. The inverse is where you don't swap them and you negate them. If not P, then not Q. And the converse is where you flip them but don't negate them. if Q, then P. So what have we got here? If this is true, then this is true. And then here, what do? We negate them both, but we don't flip them. So that would make it the inverse. Okay. Write the contrapositive of the given statement and then determine if the contrapositive is true. Well, the contrapositive here, if the graph of this is an oblique line, then m is not equal to 0. The contrapositive would be if m is equal to 0, then y equals mx plus b is not an oblique line. Well, oblique, I think in this context, means that it's slanted. And if m is equal to 0, it's horizontal. It's not slanted at all. So no, the contrapositive is not true, which actually means this statement isn't true either. If a quadrilateral has two sides of equal length, then the quadrilateral has two angles of equal measure. The contrapositive would be if the quadrilateral does not have two angles of equal measure, then it does not have two sides of equal length. Well, I don't think that's true, but let's see if we can draw an example where what do we have to do in order to get if the quadrilateral does not have two angles of equal measure, then it does not have two sides of equal length. If the quadrilateral has two sides of equal length, then the quadrilateral has two angles of equal measure. If it does not have two angles of equal measure, then it does not have two sides of equal length. In order to find a counterexample to this, something that negates this, then I would have to find something where this is true, right? Which would be the quadrilateral does not have two angles of equal measure, but it does have two sides of equal length. So let's give it two sides of equal length here and here, just for fun. What if I did this? Right, where this meets here, this goes here. Pretty clearly that does not have two angles of equal measure, but it does have two sides of equal length, and it is a quadrilateral. I guess basically what I've done here is something unexpected. I have created a concave quadrilateral. Okay, so here I've got two sides of equal length, but no two angles are the same. So I have, right, the quadrilateral does not have two angles of equal measure, and it does have two sides of equal length. So that means the contrapositive is not true, and it means the original statement is not true either. The original statement said if a quadrilateral has two sides of equal length, which this clearly does, then the quadrilateral has two angles of equal measure, which this does not. And so that makes number 8 false as well. The converse and inverse of if it rains today, then it will rain tomorrow. The converse is where you just flip them. If it will rain tomorrow, then it rains today. That would be the converse. And the inverse is where you just negate them both. If it doesn't rain today, then it won't rain tomorrow. That would be the inverse. Given the statement two supplementary angles are congruent if and only if they are right angles, the two if-then conditionals would be if two supplementary angles are congruent, then they are right angles. And the other way around would be if two angles are right angles, then they are supplementary angles that are congruent. And then use substitution on the definition of logarithm to complete this. If 2 to the 5th is equal to 32, then the log of 32 base 2 is equal to 5. That brings us to the end of those.